Another day, another story. During the 1970s and 80s, the phenomenon called acid rain was one of the most well-known environmental problems in Europe and North America, appearing frequently in news features and mentioned, on occasion, in situation comedies of the day. Since that time, the visibility of acid rain in the media has been supplanted by stories about climate change, global warming, biodiversity issues, and other environmental concerns. Acid rain still occurs, but its impact on Europe and North America is far less than it was in the 1970s and 80s, because of strong air pollution regulations in those regions. The term acid rain is a popular expression for the more formal and scientific term acid deposition. Welcome to Tabo Eminent Channel. Acid deposition includes more than just acid precipitation in the form of falling rain. Acid deposition can occur as snow, sleet, hail, and fog, too, and it also includes dry deposition, made up of acidic particles and gases, which can affect landscapes during rain-free periods. Precipitation of each of these forms is considered acidic if it has a pH of about 5.2 or below. Water with a pH of 7 is neutral, however, rainwater and surface water lean slightly acidic. The excess acids often come from human activities, particularly from the burning of fossil fuels, coal, oil, natural gas, and the smelting of metal ores, and also from volcanic activity. Sulfur dioxide, SO2, and nitrogen oxides, NOx, the combination of NO and number 2, are the chemical compounds that are most responsible, produced in the U.S. mostly through the burning of coal by electrical utilities. Where industrial emissions are large and emission controls too weak to reduce SO2 and NOx emissions, acid deposition will fall hours or days later, far downwind of power plants and other emission sources. In these areas, the pH of precipitation can average between 4.0 and 4.5 annually, and the pH of individual rainstorms can sometimes drop below 3.0. In addition, cloud water and fog in polluted areas may be many times more acidic than rain falling over the same region. If the precipitation falls in acid-sensitive areas, that is, areas without acid-neutralizing chemicals such as limestone, which acts as a buffer to acidic conditions, as long as the supply of limestone in the environment lasts, the pH of the water and the soil decreases, bringing heightened risk to many forms of life. Acid deposition can reduce the pH of surface waters and lower biodiversity by contributing to a decline in the health of fishes and invertebrates. It weakens trees and increases their susceptibility to damage from other stressors, such as drought, extreme cold, and pests. Acid rain can also leach important plant nutrients, such as calcium and magnesium, from the soil and release aluminum, bound to soil particles and rock, in its toxic dissolved form. Acid rain that falls in urban areas contributes to the corrosion of surfaces exposed to air pollution and is responsible for the deterioration of limestone and marble buildings and monuments. The acid rain problem in Europe and North America has largely abated because of stronger SO2 and NOx emission controls, such as the U.S. Clean Air Act of 1970, the Canada-United States Air Quality Agreement in 1991, and similar measures in Europe. In the United States, the first phase of emission reductions took effect in 1995, and subsequent reductions followed. Such effective emission controls have not spread to all countries, however. As developing countries such as India and China have industrialized, their emissions of SO2 and NOx have increased. This same pattern can be observed in some of the quickly growing urban areas in Latin America and Africa, which has resulted in more acidic rain and other acid deposition falling both within and downwind of those regions. Acid rain, a significant environmental issue in the latter half of the 20th century, has somewhat diminished in severity due to global efforts to reduce emissions of sulfur dioxide, SO2, and nitrogen oxides, NOx. These pollutants, primarily emitted from industrial activities, vehicle exhausts, and power plants burning fossil fuels, used to combine with atmospheric moisture to form sulfuric acid and nitric acid, leading to acid rain. Various measures have been implemented to combat acid rain, including the installation of scrubbers and catalytic converters in industrial plants and vehicles, respectively, to reduce emissions of sulfur dioxide and nitrogen oxides. Additionally, the adoption of cleaner energy sources such as natural gas and renewable energy has contributed to the decline in emissions. However, while significant progress has been made in reducing acid rain in many parts of the world, it remains a concern in certain regions where industrial activity and pollution are still high. Moreover, other environmental issues such as climate change continue to pose challenges to ecosystems and the planet's overall health. Ongoing monitoring and efforts to mitigate pollution are essential to continue the trend of reducing the impact of acid rain. The story of acid rain is a testament to the power of global cooperation and environmental awareness in tackling pressing ecological challenges. In the mid-20th century, as industrialization surged and fossil fuel consumption skyrocketed, the unintended consequence of acid rain began to manifest. Emissions from factories, power plants, and vehicles released vast quantities of sulfur dioxide and nitrogen oxides into the atmosphere. These pollutants combined with atmospheric moisture to form sulfuric acid and nitric acid, which fell back to Earth as acid rain, snow, fog, or dust. The environmental impact was severe. Acid rain devastated forests, corroded buildings and infrastructure, polluted waterways, and harmed aquatic life. Lakes and rivers became acidic, leading to the decline or extinction of fish species and other aquatic organisms. Forests suffered from weakened trees, diminished growth, and increased vulnerability to pests and diseases. Recognizing the urgency of the situation, countries around the world began to take action. The Clean Air Act in the United States, enacted in 1970 and strengthened in subsequent years, set emissions standards and regulations to control air pollution, including sulfur dioxide and nitrogen oxides. Similar measures were implemented in Europe and other regions facing the acid rain crisis. Technological advancements played a crucial role in combating acid rain. The development and widespread adoption of scrubbers, which remove sulfur dioxide from industrial emissions, and catalytic converters in vehicles, which reduce nitrogen oxide emissions, helped to significantly curb pollution. Furthermore, international agreements such as the 1979 Geneva Convention on Long-Range Transboundary Air Pollution and its subsequent protocols provided frameworks for countries to collaborate on reducing air pollution and mitigating its effects. Through these agreements, nations work together to limit emissions and protect ecosystems from the damaging effects of acid rain. As a result of these concerted efforts, the severity of acid rain has diminished in many parts of the world. Rivers and lakes have begun to recover, and forests have shown signs of regeneration. However, the story of acid rain serves as a reminder that environmental challenges are complex and ongoing. Continued vigilance, research, and action are necessary to ensure that the progress made in addressing acid rain is sustained and that other environmental issues are effectively addressed. However, the story of acid rain is far from over. While significant progress has been made, challenges remain, particularly in regions where industrialization continues to outpace environmental regulation. Moreover, the legacy of acid rain persists in the form of damaged ecosystems and ongoing threats to biodiversity. Thanks for watching. Request you to subscribe the channel.